is Kübra. Kübra is an assistant professor of industrial engineering at Koch University since 2023. She has received her PhD degree in industrial engineering in Quadratic University in 2022. In her PhD research, she addressed bilevel optimization related to information spread over the social networks in a competitive network. She worked as a postdoc researcher at the Institute of Production and Logistic Management at Johannes Kepler University, Linz, from 2020 to 2022. Her research interest spans across bilevel optimization, interdiction games, inference spread on networks, and designing algorithms for discrete optimization. Thank you for accepting our invitation, Kübra, and the floor is yours.
Thank you, Nagisa, for the introduction, and also thank you for organizing this webinar and the invitation. Yeah, I should have shared the presentation. Can you see it now?
Yes, it's perfect.
Yes. Okay, great. Hello, everyone. I will be presenting our ongoing work, joint work with Elizabeth Gar, John Lee, Ivana Liobic, and Marcus Sinal on integer bilevel programs with quadratic lower level problems using disjunctive cuts. Yeah, this is the outline of my talk. I will first introduce our problem. Then I will describe how to use disjunctive cuts for the specific problem structure we have, describe our solution algorithm, and give some numerical results, computational results. Let me start with the problem definition. This is the integer nonlinear bilevel problem that we are dealing with. This the upper level of this problem is an integer linear program. The lower level is a quadratic integer linear program, and we have these linking constraints in the lower level, and the Q of the objective function of the lower level problem is a quadratic function, and the constraints in both upper level and lower level are linear constraints. And these are the properties, the sizes of our parameters. We have N1 leader variables and 2 follower variables, or you can also call upper level and lower level variables. And we have this quadratic cost matrix R, and the linear component of the follower objective G. And our assumption is that the coefficients in the lower level, in the followers problem, they are all integers. This is the assumption that we have on our problem parameters. And I'm almost sure that the audience is familiar with, all of the audience is familiar with the value function reformulation. But to be complete, when we take all the constraints of the upper level and the lower level and ignore the followers objective function, and instead we enforce a constraint telling that the Qy, the objective function of the follower, must be as good as the optimal value of the followers problem for the given leader solution. This is the value function reformulation. So phi of x is the optimal value of the followers problem. And if we drop the value function constraint, which is the last constraint, we get the high point relaxation of the overall problem. So it's a relaxation because we drop the optimality condition of the follower solutions. And we denote by big omega the shared constraint set of the problem. So we have all the constraints of the upper level and lower level. And the bilevel set of bilevel feasible points is denoted by F. And here we need that the shared constraints, all of the shared constraints are satisfied by the point xy, and y must belong to the rational reaction set of the follower. So y must be an optimal response for the given x. What do we know about this problem? Starting from linear version, I mean mixed integer linear version of this problem, without any non-linearities, we know that it is sigma 2p hard. And among other solution methods, we have two well-known methods, state-of-the-art methods, Fischetti and others, and Wang and Zhu. The first one is an intersection cut-based branch and cut algorithm. The other one is called the watermelon algorithm, and they are both based on the idea of separating bilevel-infeasible solutions from the problem's feasible region, feasible region of the high point relaxation, actually. And by bilevel-infeasible points, we refer to, we mean the points that may satisfy the shared constraints, but they fail to satisfy the optimality condition of the follower. When we come to the methods, existing methods for integer nonlinear bilevel programs, we have some methods which cannot handle the current structure we have, the quadratic lower level. And we have some general purpose method like the method by Metzos and the Kleinetti and Ajiman. These are general purpose methods, but they are not very scalable, very efficient, and their practical performance is limited to very few variables. We have the SOCP-based, the second-order conic programming-based disjunctive cut approach by Gar and others. And in this previous work of ours, we assume a convex follower objective function, so it cannot handle the current setting as well. In this work, we want to design an algorithm for the current problem setting, ILP, QILP setting, using disjunctive cuts. And we want this algorithm also to be able to handle non-convex lower level objective function. We will make use of disjunctive cuts, which were introduced by Ballas initially. They were frequently used for mixed integer nonlinear programs, and to a limited extent, they were used for bilevel problems. Okay. The idea of an improving direction was used in some earlier works, such as the work by Wang and Xu and Fischetti and others. And there, the objective function of the lower level is linear. So under the assumption that R matrix, R coefficients are 0, a direction, improving direction delta y, such that G times delta y is negative, the following set, following polyhedron, does not contain any bilevel feasible point. The meaning is of this proposition is that if you have a delta y vector such that y plus delta y still satisfies the linking constraints of the lower level, and G times delta y, which is the contribution of delta y to the follower objective, is negative, and we have a minimization problem, then xy cannot be bilevel feasible because x and y plus delta y is a better and feasible solution for the follower. So y cannot be an optimal response to x. And what we call an improving direction here is denoted by delta y. We want to use this idea, we want to extend the idea for the quadratic case, quadratic lower level objective. We don't impose any restriction on delta y, except it is an integer vector. And for a given delta y, the set x of delta y is defined as what we can see here. The conditions of this set tells us that y plus delta y must satisfy the linking constraints and the lower and upper bounds of the object follower problem, and y plus delta y must be a better solution in terms of follower objective compared to y. And as a result, xy cannot be a bilevel-feasible point. So our set x of delta y is a bilevel-free set. When we extend the previous set that we see here, the set x, we extend the set and denote it by x plus of delta y. The interior of this set does not contain any bilevel-feasible point in its interior. It's based on the integrality assumptions of the coefficients, actually. We assume that all of the parameters in the follower problem, lower level problem, they are integers. So this is an extension of the previous set. So interior of x plus is x. And I already explained that the interior of the set cannot contain any bilevel-feasible points because y plus delta y will be a better solution than y itself. In the previous work, where we used SOCP based disjunctive cut, the bilevel-free set considered was not a polyhedron, although fewer inequalities are needed to define the bilevel-free set. Here, we need to include both the linking constraints in the lower level and lower and upper bounds on the follower variables. These are also needed to define the bilevel-free set because of using a relative bilevel-free set, not an absolute one. We use an improving direction instead of an improving solution. Okay, it's bilevel-free, so it cannot contain any bilevel-feasible points in its interior, but where are the bilevel-feasible points? They are in one of these disjunctions, actually, disjuncts. We have 4 of them due to the definition of our bilevel-free sets. Each inequality here corresponds to one type of disjunction. The first one is the objective disjunction, or disjunct, maybe it's a better use. And if you expand this inequality, we see that the quadratic terms on the variables cancel out. So we have a linear inequality here. And second type of disjunct is the follower linking constraint disjunct. And then we have lower bound and upper bound disjuncts. And the union of these all these disjuncts, they contain our bilevel-feasible points. And what we want to do is to separate bilevel-infeasible points from the above union. And since all of our disjunctions are linear, we can do the separation of bilevel-infeasible points by solving an LP, which we call a cut-generating LP, because this is basically due to the fact that the bilevel-free set is a polyhedron and the disjuncts are all linear inequalities. Okay, I'm not going to the details of the cut-generating problem, but I just want to summarize the idea, the standard approach used in disjunctive cuts. We want to separate our points, bilevel-infeasible point, x star, y star, from the union of the disjunctions. So we want, in the primal formulation, the idea is to write down the point as a convex combination of points from each disjunct. And for this, we define the xk variables, xk and yk, and we define some weights for each point. These are denoted by lambda k, and we abuse the notation a little bit. Let me show you. Yes, I can show you. that we need to define different dual variables for each type of each disjunctive types that I have just described. And we have the objective disjunction, the linking constraint, the lower bound and upper bound constraints. So our points xk, yk, they need to satisfy the constraints of the associated disjunction k. And this is the cut generating dual problem. The objective is to maximize the violation of the cut at point x star y star. And we have constraints for each of the disjunctions. And we need a normalization constraints in our cut generating dual problem. And we adopt the standard normalization condition, which means that the sum of the all dual multipliers except the cut coefficients, they must sum up to 1. And this is the this is how the real cut generating problem looks like. Okay, the solution algorithm. Before designing the algorithm, we wanted to answer the question, do we really need all of these disjunctions? Do we really need all of them in our cut generating problem? And it turns out that we don't need all of them, as one may expect. Starting with linking constraint disjunctions, if bi times delta y is non-negative, then there cannot be any feasible solutions in this disjunct. So this disjunct is redundant. The I delta y is redundant. For lower bound and upper bound disjunctions, if delta y is non-negative, then the corresponding lower bound disjunction is redundant, because with non-negative delta y, any y plus delta y will not satisfy the lower bound conditions, so it will not be feasible. Therefore, the disjunction is empty. And for upper bound, for any non-positive delta y, we can label the associated upper bound disjunction as redundant. And removing redundant disjunctions are helpful in the sense that, we can make the bilevel-free set larger, so we can get stronger cuts, possibly, when we get rid of some of the disjunctions. So we can formulate an MINLP to determine an improving direction while maximizing the amount of redundancy, the number of redundant disjunctions, following the idea also used by Fischetti and colleagues. We consider two separation problems. In the objective function, we actually try to maximize the amount of redundancy by minimizing the slacks of the lower level constraints, the follower constraints. And all of these constraints, they are there to guarantee that x star and y star plus delta y is a feasible solution, and delta y improves over y star. So y star plus delta y has a better objective value. The first constraint in both formulation is a nonlinear constraint because of the quadratic objective value. The others are linear constraints. So in the first one, we use the L1 norm of slacks. So we use continuous slack variables. And in the second one, we use binary slack variables to indicate if the disjunction is redundant or not. And we propose a branch and cut algorithm, solve the high point relaxation, and separate bilevel-infeasible points via disjunctive cuts. And for disjunctive cuts, we can either solve the previous separation problems, the MINLPs, to get an improving direction directly, or we can solve the follower problem for the given leader solution, which is basically the feasibility check problem, and get an improving solution if it exists. And then from the improving solution, let's say by hat, we get an improving direction. This is another method that we can follow. Or we can use a heuristic, make use of a heuristic separation method. Here, what we do is we employ a pool of previously generated improving directions, because we observed that generating improving directions can be very costly, time-consuming. And pool directions are used if the direction will give us a feasible solution and the objective value is input in that direction. And we expand the pool with the solutions of our exact separation problems. Okay, I need to wrap it up. In our computational study, we use the test set from our earlier work. And in that test bed, we have the quadratic bilevel covering problem instances, which we denote by QBCO, quadratic bilevel multiple knapsack problem instances, QBMKP, and we generate additional constraints, additional instances with more linking variables in the lower level, which means that we have more disjunctions. And we consider the bilevel quadratic knapsack problem instances, which have non-convex quadratic objective function by Zeneros and others. In this one, in this particular problem, the leader has a single variable which determines the capacity of the knapsack, and the follower wants to maximize the profit, which is a quadratic function. Our settings are L1 when we solve this separation problem for L1, separation problem for L infinity, and we can solve the follower problem to optimality to get improvement direction. We can solve the follower problem greedily, which is denoted by FG, and we have the benchmark methods, the SOCP methods by GAR and others. And we also denote by this IF addition that we separate both integer and fractional solutions. And we use simplex for solving any ILP, LP, MIN, LP, and everything. Yeah, these are the results for 280 binary instances. And we have 5 methods, as you can see. The SOCP method, purple squares, the benchmark is somewhere in the middle. When we look at the number of instances, the runtime of our instances. The FO option, solve the follower problem optimally, is the worst. And both L1 and L infinity options, the separation problems, they perform much better compared to the other settings. Also in terms of optimality gaps at the end of the time limits, 10 minutes time limit. And here I also have some interesting results to quickly show, because for different instance sets, we can see that the solution times for the benchmark methods are much larger. But when we look at the number of integer cuts and fractional cuts in these 2 columns, we see that the new methods, the disjunctive cuts, are stronger because we can solve the problems optimally with a significantly fewer number of cuts. And also the number of branch and bound nodes explored are significantly smaller compared to the benchmark methods. And we can solve more instances optimally for more complicated problems, the multiple knapsack problems. For the instances with non-convex lower level, it turns out that solving separation L1, L-inf problems is very inefficient, because there we have non-convex quadratic constraints, and the solver cannot handle it. You need some conversions, etc. Even after that, the performance is very bad. but solving the follower problem for separation, for finding an improving solution, and thus an improving direction, is much more efficient. And in our initial test set, we have 80 instances, and 70 of them are solved optimally within the time limit. And we are able to find a feasible solution for almost all of them, but 3 instances only. We still need to do the benchmarking with the bilevel linear solver of Fischetti and colleagues, because it is possible to linearize our instances using McCormick transformation and then solve via a linear solver. We will see how it will perform with that. Yeah, we propose a new exact method for ILP, QILP type bilevel problems. We show that the bilevel-free set we considered they are polyhedral sets, and our quadratic problems are LPs, and it outperforms the existing methods on convex instances, and it can also handle convex lower level objectives. Thank you for your attention. I exceeded the time. Sorry about that. Thank you.